Tonight, far above the quiet streets of your city, an aging spacecraft over Mars has just seen something that should not exist. Tianwen-1, China's first mission to the Red Planet, has been circling Mars for years, its main job long finished. But its cameras are still watching, still listening to the darkness. And in that darkness, they have found a visitor from another star. Astronomers call it 3I Atlas, only the third confirmed interstellar object we have ever seen, and possibly older than the Sun itself. It is small on a cosmic scale, just a few miles across, but it refuses to behave like an ordinary comet. No bright sweeping tail, no familiar pattern of dust and gas. Instead, it glows like a compact, blurry star, shifting in brightness, pushing against invisible forces as it cuts through our solar system. On paper, it is just another icy body from deep space. In practice, it is a collection of unlikely behaviors stacked on top of each other. A strange path that lies almost perfectly in the plane of the planets. A motion that seems to speed up without a clear engine. A chemistry that hints at violent ancient places, beyond the time when our own world even existed. Tonight, we are going to slow down and follow Tianwen-1's gaze. We will unpack what this lonely probe around Mars has really seen. Why some scientists quietly wonder if 3I Atlas comes from the dawn of the universe, and what it means for a species that has just begun to look outward. No panic, no doom, just a careful, steady journey into one unsettling question. And you are watching it from a blue world that it barely notices. What do you do when the oldest thing in the room suddenly looks back at you? Tonight? For years, Tianwen-1 has circled Mars in a steady, silent path. Its main mission ended long ago, its lander asleep on the dusty plains below, its instruments running on borrowed time. Yet the orbiter remains awake, drifting through the thin Martian halo, like an old lighthouse still sweeping the sea. No one expected it to make any more discoveries, and certainly not this one. From its vantage point above Mars, Tianwen-1 sits in a rare pocket of space where sunlight, geometry, and timing briefly align. When 3I Atlas slipped behind the Sun from Earth's perspective, every telescope on our planet went blind. The object was simply swallowed by solar glare. But from Mars, the Sun sits in a different place in the sky, and at the precise moment when Earth lost sight of 3I Atlas, Tianwen-1 was drifting into a clear line of sight, an open window measuring only days. Through that window, at a distance of roughly 18 million miles, Tianwen-1 captured something no human eye could see. A dim, ancient traveler, moving with purpose through a part of the sky where comets should not be. Not a streak, not a classic plume, but a concentrated blur of shifting light, a familiar stranger behaving in an unfamiliar way. The remarkable part is that none of this was planned. China did not send Tianwen-1 to study interstellar visitors. It was meant to explore a neighboring world, not witness something older than the Sun. Yet timing placed it in the right position, at the right hour, with the right instruments still functioning. For a brief moment, the spacecraft launched for one purpose became the only functioning eye on a cosmic mystery passing by. Scientists often talk about serendipity, those rare events where nature writes a story no one predicted. This was one of them. A single orbiter around another planet became the only witness. A moment that will not happen again in our lifetime. No human eye will ever see it this close again. And that is why astronomers across the world paused when the images arrived. The alignment was not just unusual, it was historic. As one researcher described it, this was a once-in-human-history alignment. The question now is simple and impossible to ignore. But what exactly did Tianwen-1 see? When Tianwen-1 captured its faint silhouette, astronomers quickly realized they were not looking at something born in our neighborhood. 3I Atlas belongs to a tiny, almost mythical class of visitors, true interstellar travelers. Before it came, only 2 others had ever been confirmed. In 2017, the oddly shaped Oumuamua swept past us without warning, leaving more questions than answers. 2 years later, the icy comet Borisov arrived, carrying the unmistakable fingerprints of a world not our own. And now, a third, a fragment of deep time, wandering through the space between stars before slipping quietly past Mars. The clue that it came from elsewhere lies in its speed. 3I Atlas is moving faster than the sun's gravity can hold. Its velocity is a clean, unmistakable signature of origin. It did not form here. It is simply passing through. Every world in our solar system is bound to the sun's pull. But this object is not. It enters, crosses our domain, and will leave again, never to return. Only something that began its journey light years away can move with such freedom. But the deeper revelation came when scientists analyzed the faint chemical cues reflected in its light. That analysis pointed to something extraordinary. The material inside 3I Atlas does not match the chemistry of planets and comets born in the last 5 billion years. Instead, it resembles the enriched metal-heavy debris forged by the universe's earliest stars. Stars that lived fast, died explosively, and seeded the cosmos with elements that did not exist at the beginning. Among those elements is nickel, and 3I Atlas contains far more of it than any ordinary comet should. Nickel abundance is a kind of cosmic timestamp. Only the first generations of stars, the so-called population 3 giants, produced that pattern in meaningful amounts. They dominated the dawn of the universe more than 13 billion years ago, when galaxies were young and the cosmic background light had barely faded from the Big Bang. When those ancient stars collapsed, they scattered their remains into interstellar space, forming the raw material that would one day become new worlds. 3I Atlas appears to be one of those raw pieces, a shard from the time before the sun existed, before Earth had formed, before our galaxy had fully taken shape. To say it is old is an understatement. Everything familiar to you, your planet, your oceans, your mountains, your cities, is younger than this object. Every culture, every story, every fossil, every continent is a recent event compared to it. This object is older than everything you have ever known. It is a surviving ember from a universe that barely resembles the one we see today. And yet the marvel is not only its age, but its endurance. How does a fragment forged in the chaos of the early cosmos remain intact after 13 billion years? How many gravitational tides has it survived? How many stars has it passed? How many close calls with distant worlds? Every mark on its surface is likely a record of a place and time we can barely imagine. As one researcher quietly put it, we were looking at something from the dawn of time. The truth is simple. 3 Atlas is not just another visitor. It is a messenger from the universe's first chapter, carrying clues about the worlds that came long before ours. And if its age alone is astonishing, the real intrigue begins when we examine what it is doing right now. And from here, the anomalies only grow. When the first measurements of 3I Atlas came in, astronomers prepared themselves for the familiar features of an active comet a glowing coma, a sweeping tail, a dusty trail stretching behind it like a slow exhale. That is what happens when sunlight strikes ice. It vaporizes, gas escapes, dust scatters. The result is one of the most reliable signatures in planetary science. A comet without a tail is like a storm without wind. It simply should not exist in nature. But 3I, Atlas, refused to follow the script. As it approached the sun, instruments detected a measurable loss in mass, more than 13% of its total body. That is roughly 4 billion tons of material, enough to fill mountain ranges. In any normal comet, that loss would erupt into space as plumes, streaks, jets, or at the very least a faint, widening spray. Yet Tianwen-1 saw none of it. No tail, no plume, no haze, not even the thinnest ribbon of dust across the black. Scientists checked everything. They examined the angle of observation. No issue. The geometry around Mars was ideal. They checked the camera, functioning perfectly. They checked the exposure, the filters, the background stars. Nothing about the spacecraft or the environment could hide 4 billion tons of missing matter. Gas and dust, once released, scatter light easily. Even a thin thread of particles would glow under solar radiation. But the images remained clean, empty. The object looked almost polished, a smooth blur with no visible shedding. That left the uncomfortable conclusion. The mass was disappearing, but not in any way we understand. If the material escaped, it did so without leaving a visible mark. If it sublimated, it did so without detectable vapor. And if something was suppressing or absorbing the outflow, we do not yet know what. This was not a simple case of a weak tail or a hidden angle. This was the absence of every expected physical signature. For many researchers, this was the moment the puzzle deepened. Comets are messy. They crumble, sputter, and scatter dust for millions of miles. Even the tidiest examples leave behind a detectable trail. Dust lingers for years, drifting in long arcs behind them. But 3I Atlas left nothing. Its exterior remained strangely uniform, its profile unusually compact, as if the surface itself resisted shedding. Not because it was inert, because we know it lost mass, but because the released material was not behaving like any known cometary outgassing. And so the question grew sharper. 4 billion tons went somewhere. Where? Did it vent gas that instantly ionized? Did it eject dust in a form that failed to interact with sunlight? Or is there a mechanism hidden from our instruments that releases mass without producing a visible signature? Something is absorbing or hiding the outgassing. The smoothness of 3I Atlas only adds to the tension. Real comets are rugged, irregular bodies shaped by billions of years of freezing and thawing. Their surfaces fracture and break. Their jets carve uneven pits. But the distant outline Tianwen-1 recorded looked almost too uniform, as if long ages in interstellar space had polished it into an aerodynamic shard, a shape built to shed mass silently. For a moment, astronomers stepped back and reconsidered what they were seeing. An interstellar object older than the sun should be battered, scarred, and unstable. Instead, it was shedding unimaginable amounts of material without leaving any visible footprint. If age had shaped it, it had shaped it into something that behaves differently from anything in our experience. And yet, the missing mass wasn't the only mystery. As the data from Tianwen-1 was processed, another puzzle surfaced, one that felt even more unsettling than the missing tail. Instruments showed that 3I Atlas was gaining speed as it moved away from the sun. Not dramatically, not violently, just a gentle, measurable push that nudged it slightly faster than gravity alone would allow. A small deviation, but unmistakable. In the world of orbital mechanics, even a tiny drift carries enormous meaning. Under normal circumstances, this effect has a simple explanation. When comets warm, jets of vapor escape from their surface. These jets act like miniature thrusters, giving the comet a tiny shove. This is called non-gravitational acceleration, and it is expected. It is ordinary physics. But here, the ordinary ends, because a comet that accelerates must be venting gas, and a comet that vents gas must have a tail. 3. Atlas has neither. No plumes, no jets, no dust, no vapor. Nothing that can serve as the source of the extra momentum. The object looks smooth, compact, and strangely silent. Yet the acceleration persists. The numbers are clear, consistent, and reproducible. Every time researchers ran the calculations, the result returned the same. 3 Atlas was being pushed by something invisible. This is where memories of a previous encounter return. In 2017, Oumuamua, the first known interstellar visitor, displayed an almost identical behavior. It, too, sped up slightly as it left the sun. It, too, produced no detectable outgassing. And it, too, forced astronomers to confront the uncomfortable possibility that something was generating motion without leaving physical traces. Some argued it was exotic ice sublimating. Others said the data was incomplete, but the acceleration remained. And now, years later, a second interstellar object is repeating the same impossible pattern. This time, however, the measurements are clearer. Tianwen-1 captured multiple passes, multiple positions, multiple confirmations. The acceleration fits the mathematical profile of a non-gravitational force, but the force itself is absent. No mechanism appears in any wavelength. No dust brightens the space around it. No plume interrupts the darkness. The effect is real. The cause is unseen. For scientists, this is deeply frustrating. Physics demands an explanation. This object refuses to give one. When nothing is pushing it, why is it moving faster? Is the material escaping in a way that refuses to scatter light? Is the surface releasing energy in a form we cannot detect? Or is the structure of 3I Atlas built from something that reacts to sunlight in a way unlike any comet we have ever studied? The parallel with Oumuamua keeps the debate alive. One mystery is strange. Two mysteries are harder to ignore. Both are interstellar. Both behave in ways no native object ever has. Both challenge the same assumptions about motion, mass, and sunlight. Unseen forces are acting on it. The question is whether those forces come from within the object or from something deeper in its design. And the uncertainty does not end there. Because whatever is pushing 3I Atlas is also guiding it along a path that seems impossibly precise. And even stranger, Atlas chose the perfect path through our solar system. In the vastness of three-dimensional space, an interstellar object can approach from absolutely any direction. Above the solar system, below it, at steep angles, sideways paths, or trajectories that slice through like a needle thrown across a room. The sky is open in every dimension. That is why astronomers expected 3I Atlas to arrive from some random orientation, a direction uncorrelated with the structure of our planets. But it didn't. Instead, 3I Atlas slipped into the solar system along a path lying almost perfectly inside the ecliptic, the thin, 5-degree-wide plane where nearly every planet orbits, where most spacecraft travel, and where our observational coverage is strongest. The probability of an interstellar object naturally aligning with this narrow slice of space is vanishingly small. Roughly 0.2%, less than the odds of flipping a coin and having it land on its edge. And yet, that is exactly what happened. 3I Atlas approached on the precise highway where we keep our cameras. A plane crowded with probes, orbiters, and telescopes designed to monitor the movements of worlds. It did not arrive from the polar regions of the solar system, where geometry would have hidden it from our view. It followed the only path that maximized the chance of being detected, tracked, and imaged by multiple instruments, including Tianwen-1, MAVEN, Mars Express, and even Earth's ecliptic-based surveys once it emerged from behind the sun. The effect is startling when you picture it in 3 dimensions. Imagine the solar system as a thin, flat disk floating in space. Now, imagine the rest of space as a sphere surrounding that disk, a sphere from which a visitor could originate from any direction. For 3I Atlas to thread itself through the narrow disk, instead of the remaining 99.8% of available angles, feels almost intentional. Too clean, too convenient, too aligned with our line of sight. This wasn't random. Not in appearance, not in angle, not in timing. As one researcher put it, it arrived on the exact plane where we keep all our cameras. For astronomers who had just watched the object accelerate without a visible cause, this new detail only sharpened the tension. Why would the third interstellar visitor we have ever seen enter along the single path where we can observe it best? That question lingers because the ecliptic plane is not just a geometric convenience. It is the route every probe and survey uses to monitor the planets. It is our traffic lane, our science corridor, our observational backbone. Any object that enters along it is guaranteed maximum attention, and for 3I Atlas, the coincidences didn't stop there. When researchers first reviewed the processed frames from Tianwen-1, they expected the same thing every comet displays when sunlight heats its surface. Particles streaming outward, pushed away from the sun by radiation pressure and the solar wind. This is one of the most reliable behaviors in the entire solar system. Dust moves outward, gas moves outward. Every physical model agrees on this. But 3I Atlas broke that rule. Subtle patterns in the scattered light suggested something impossible. Tiny particles appeared to be drifting not away from the sun, but toward it. At first, teams assumed an artifact, maybe an angle issue, maybe a processing error, maybe background noise aligning in a deceptive way. Yet, as more frames came in, as more teams around the world ran the same analysis independently, the conclusion converged. The movement was real. It was happening. And it made no sense. Under the laws of solar radiation physics, a sunward jet should not exist. The constant outflow of charged particles from the sun creates a pressure that always pushes material outward. Even in rare and chaotic jets, the debris still bends away from solar influence. But images of 3I Atlas showed a faint, narrow line of activity angled inward, as if something on the surface was releasing particles against the direction of solar pressure. Not just sideways, not just irregular, directly toward the sun. Nature doesn't do that. Something else is at play. The deeper scientists looked, the more troubling the pattern became. No known comet in the recorded history of astronomy has ever displayed a sunward jet. Hundreds of studied comets, thousands of documented outgassing events, and not one instance of a sustained inward plume. Even Oumuamua's unexplained acceleration never showed anything resembling this. The motion of its dust, or lack of dust, remained consistent with outward pressure. The inward drift of particles around 3I Atlas is not simply unusual, it is unprecedented. And the effect persisted across multiple observations, different orbits, different angles, different processing systems. Every serious attempt to disprove the sunward motion fell apart under scrutiny. It was not an illusion of lighting, not a side effect of instrument wobble, not a quirk of background stars. Something on or within 3I Atlas was producing a directed flow that behaved as if it were immune to the sun's outward force, or stronger than it. This is where the questions deepen. What mechanism could generate a jet powerful enough or structured enough to push particles inward? What material could react to sunlight by pulling toward the star instead of fleeing from it? And why would an ancient object from interstellar space display an orientation so tightly aligned with solar direction? If this is chemistry, it is chemistry we do not yet understand. If it is structure, it is a structure unlike anything found on a natural comet. For astronomers, the reaction is a blend of shock and unease. The behavior feels wrong, as if the object operates by rules unfamiliar to our solar system. The longer researchers watched the data accumulate, the more it felt as if they were witnessing a pattern designed for a purpose. Not a random sputter of dust, but a directed, sunward expression of energy. The growing suspicion is simple. The sunward jet is a clue, and not an isolated one. It ties directly into the strange light polarization that appears later in the data. Another signal that something about its surface and structure bends physics in unexpected ways. Its size only makes the puzzle bigger. If 3I Atlas were small, many of its strange behaviors might be easier to tolerate. Tiny objects are volatile. They tumble. They heat quickly. They drift under subtle forces. But 3I Atlas is not small. Estimates from brightness, thermal modeling, and distance place its core at roughly 5 to 6 kilometers across, more than twice the size of Borisov, the largest confirmed interstellar comet ever observed. It is a mountain drifting through space, a cold, ancient monolith forged before the sun existed. Objects this large are supposed to be slow. That is one of the quiet rules of celestial mechanics. Big bodies carry inertia. They respond sluggishly to forces. They lumber through the void like massive ships on a dark ocean. But 3I Atlas breaks that rule. Its incoming velocity was already high, but its outgoing speed, the speed measured after its encounter with the sun, is even more remarkable. Faster than Oumuamua, faster than typical long-period comets, faster than predictions based solely on gravity and thermal physics. In fact, when the numbers are compared statistically, the combination of size and speed makes 3I Atlas a statistical outlier, a 1 in 1,000 visitor. Boys, the probability of encountering an interstellar object that is both this massive and this fast is roughly 0.1%. And that estimate assumes perfect randomness, which the previous anomalies already undermine. When a large object moves this quickly, the energy involved becomes immense. The question that naturally follows is simple. How does something so massive move so fast? The usual explanations fall apart. Comets gain speed when they fall toward a star, but their outgoing speed should reflect their mass loss and the gravity they escape. Smaller comets can cheat this rule through volatile jets that tilt and push them. Larger ones cannot. Their surfaces do not respond quickly enough. Their jets do not affect their momentum as dramatically. Yet here, a massive, ancient object accelerates with the grace of something far lighter. Astronomers ran scenario after scenario. They modeled extreme outgassing. They adjusted albedo. They modified shape assumptions. None of it reconciled the mass with the motion. The numbers refused to fit. As one researcher said, it breaks the size-speed relationship of natural bodies. And when an object defies a relationship understood across thousands of comets and billions of years of solar system evolution, it forces scientists to look harder, to ask whether they are truly observing a familiar phenomenon at all. This is why the unease grows with each new line of data. Not because the numbers are dramatic, but because they are consistent. Every piece reinforces the next. A large body that accelerates without jets, that sheds mass without a tail, that moves on a perfectly aligned trajectory, and now that carries a velocity profile inconsistent with its physical scale. These traits do not stand separately. They stack, and with each layer added, the odds of coincidence shrink. What emerges is a portrait of something that does not behave like a natural relic drifting in from deep space. Something older, stranger, shaped by forces or histories we have yet to understand. And its chemistry only deepens the mystery. When astronomers began breaking down the reflected light from 3I Atlas, they expected to find the same chemical fingerprint shared by almost every comet ever studied. A dominance of light ices, traces of carbon compounds, and a familiar balance of metals, especially the universal pair, iron and nickel. Across the cosmos, these two metals tend to appear together in consistent ratios that reflect the way stars forge elements. Iron is usually more abundant. Nickel is present, but always the lesser partner. This pattern is so stable that it is considered a baseline feature of planetary formation. But 3 Atlas did not follow that rule. Its light signature revealed something that made every spectroscopist pause. Nickel levels far higher than expected, and in some models, potentially higher than iron itself. The ratio was inverted, flipped in a way rarely seen in nature. Nickel dominance is almost impossible naturally. The finding immediately pointed to one possibility: origins in an environment far older and far more violent than anything associated with the birth of our solar system. In the universe's first billion years, the earliest generations of massive stars lived fast and died young. These so-called population 3 giants burned through their fuel rapidly, collapsed, and exploded with energies far greater than typical supernovae seen today. Their deaths seeded the surrounding space with unusual mixtures of heavy elements, including rare imbalances of nickel. If 3I Atlas carries the imprint of those ancient explosions, then its material may truly be older than the sun, older than the planets, older even than the Milky Way's settled structure. An object formed from the ashes of stars that shone at the dawn of time. That alone is extraordinary. But as researchers dug deeper, another detail emerged, one that introduced a new layer of discomfort. High nickel mixtures, especially those with certain crystalline properties, are not only remnants of ancient stars. They also appear in modern engineered materials. Advanced alloys, heat-resistant turbine components, superalloys used in jet engines, deep space applications, and high-stress environments. This does not imply anything artificial about 3I Atlas. Nature can and does produce nickel-rich structures under extreme pressures and temperatures, but the resemblance between its spectral signal and the signatures of engineered alloys was enough to make researchers shift in their chairs. A metal signature found in jet engines, found in a cosmic object predating the sun. The dissonance between age and composition is what unsettled scientists most. How does a relic from the early universe carry a ratio of elements that feels both primordial and strangely familiar? The next question struck even deeper. How did such a composition survive intact for 13 billion years? Interstellar space is not gentle. It batters objects with radiation, cosmic rays, and micrometeor impacts. Most long-lived comets erode, fracture, or lose their volatile components over time. But a high nickel structure, dense and thermally resilient, could persist far longer than typical icy bodies. Perhaps this composition is not an accident. Perhaps it is the reason 3I Atlas still exists at all. Yet the puzzle grows more complicated when examined through the lens of cometary science. Comets are born in cold, distant regions of star systems, places where metals condense slowly and remain proportionally low. High nickel content is inconsistent with icy formation zones. It suggests an object shaped in regions far hotter than any comet nursery, regions associated with cataclysm, not gentle condensation. The chemistry appears to challenge the very category astronomers placed it in. It behaves like a comet in some ways, but its composition argues for a violently forged origin. If nature made this, it did so in conditions we've never seen. Those were the words of one researcher who tried to reconcile the spectral readings with conventional models. If 3I Atlas truly formed in the aftermath of population 3 supernovae, it would be a living fossil from the universe's first age, a testament to an era when matter was still being shaped into the ingredients of future galaxies. But the resemblance to engineered materials refuses to fade from the discussion. Not because it suggests design, but because it highlights a larger truth. When nature reaches extremes, its creations can mimic human engineering. High pressures, intense heat, and unique element ratios can sculpt structures that behave in ways that feel unnatural to us simply because we have never witnessed their birthplace. It is entirely possible that 3I Atlas is nothing more than a miracle of natural physics, but a miracle forged in an environment beyond our direct experience. Still, the unease lingers. A fragment from the dawn of the universe should not look like something crafted in a forge. A 13 billion-year-old traveler should not carry a signal that mirrors advanced alloys. A comet should not contain the metal signature of heat, pressure, and structural resilience. And yet here it is, drifting past Mars, its chemistry whispering of worlds and events older than imagination. This is why scientists hesitate, why they speak carefully, why they avoid leaps beyond the data. The goal is not to jump to conclusions, but to understand an object that defies categories. The promise remains. Every anomaly will be examined with scientific discipline. No leaps, no shortcuts, only evidence. Still, the question remains open. What combination of forces, environments, and cosmic histories could produce something that looks both ancient and engineered at the same time? The answer may lie not only in its metallic composition, but in something even more surprising: the scarcity of the most fundamental ingredient in comets. But if the chemistry was strange, the water content was even stranger. One of the simplest questions astronomers ask when studying a comet is also one of the most revealing. How much of it is made of water ice? For almost every comet ever examined, the answer is remarkably consistent. Typical comets are dominated by water, often 70 to 80% by mass, with the remaining material made of dust, organic molecules, and heavier elements. This balance holds true across our solar system and across other systems we have observed through distant spectroscopy. Ice is the foundation of cometary identity, but 3I Atlas breaks that foundation completely. Early measurements suggested something was wrong, and deeper analysis confirmed it. The water content appears to be only around 4%, not 60, not 40, 4. That number is so low, it pushes the object out of the comet category entirely. With so little ice, it resembles a metallic or rocky body coated in a thin glaze of frozen material, more like an exposed core than a traditional comet. This is not what astronomers expected from something drifting through interstellar space. Comets from the outer reaches of star systems, including those from the Oort cloud, form in regions so cold that water ice becomes one of their most abundant components. Even in other star systems, the chemistry should follow the same basic rules. Cold birthplaces create ice-rich bodies. Warm birthplaces create rocky ones. A comet, with almost no water, simply does not fit the pattern. The low water content also deepens the earlier mysteries. A typical comet losing 4 billion tons of mass would erupt into a brilliant fountain of vapor. But an object with almost no water cannot outgas in the same way. The missing mass cannot be explained through the familiar behavior of sublimating ice. The mass loss must be something else: heavier volatiles, unusual compounds, or processes that do not resemble any known cometary physics. And if the material shedding off 3I Atlas is not water, its invisibility becomes even stranger. Heavy particles should scatter light more effectively. They should leave trails. They should announce themselves. But 3I Atlas stays strangely clean. The question grows sharper. Then what is 3I Atlas made of? If it is nearly dry, why does it behave like a comet? If it is dense and metallic, how does it accelerate without visible jets? Its structure begins to look more like a fragment of a planet's mantle, a hardened shard from a violent supernova, or a piece of primordial material forged in temperatures far too high for water to survive. Whatever its origin, it cannot be explained by the standard model of icy bodies drifting between stars. This is why researchers became increasingly cautious about labeling it a comet at all. Comet is a comfortable word, familiar, descriptive, evocative. But 3I Atlas resists every criterion. Too little water, too much nickel, too smooth a profile, too strange a behavior, too many missing signatures. It behaves like an icy traveler, only in the most superficial sense, while its internal nature suggests something deeper, older, and far more alien to the environments we understand. The confusion would only grow, because the next clue did not come from its chemistry or its mass. It came from something even more fundamental: the way it interacted with light. A type of signal no comet has ever shown before. Light itself provided the next clue. When traditional observations fail to explain an object, astronomers turn to one of the most subtle, revealing tools in their arsenal: light polarization. It sounds abstract, almost academic, but polarization is a kind of fingerprint. When sunlight strikes dust, rock, ice, or metal, the reflected light becomes polarized in specific ways. The angle, depth, and behavior of that polarization reveal details about the material: its grain size, texture, surface roughness, chemical composition, even how tightly particles are bound together. For 50 years, scientists have collected polarization profiles from more than 3,000 comets, asteroids, and icy bodies. The patterns vary, but they fall within known boundaries. They paint a picture of what is normal. Then came 3I Atlas, and the picture shattered. When astronomers analyzed the scattered light from this object, they found something unprecedented: an extreme form of negative polarization that does not fit any existing cometary model. Negative polarization occurs when light waves, instead of aligning in a predictable direction after scattering off dust, rotate in the opposite orientation. Most comets show a mild version of negative polarization at small phase angles. But 3I Atlas showed an intensity far beyond anything cataloged. It wasn't just unusual, it was off the charts. Polarization so extreme, it doesn't fit any existing model. At first, the results seemed unbelievable. Researchers repeated the calculations. They checked calibration. They compared data from multiple observatories. Everything lined up. The numbers refused to change. Whatever covered the surface of 3I Atlas, or whatever composed its dust, did not resemble the reflective properties of ice, carbon grains, silicates, or any combination known from comet science. This wasn't the soft, fluffy dust of a normal comet. It wasn't the dark, porous grains of primitive asteroids. It wasn't consistent with any of the materials that form in cold outer belts around stars. The extreme negative polarization suggested something else, a surface or dust environment dominated by coarse, irregular metallic grains. Not smooth metal, not reflective alloy, something ancient, something rough, something forged in violent conditions and left to harden over billions of years in interstellar space. The signal resembles what laboratory experiments have produced using samples of primitive, metal-heavy particles, materials that form in supernova ejecta before cooling into jagged, crystalline fragments. If this interpretation is correct, 3I Atlas may be coated in dust, older than the sun, older than our planets, older than almost everything around us. Material that has been drifting through the galaxy since the universe was young, preserved by the vacuum of interstellar space. But even that explanation fails to fully account for the extremity of the polarization. The numbers are simply too large, the behavior too foreign. The surface behaves as if it belongs to a different universe. Imagine looking at a comet through a filter that tells you what its skin is made of, and discovering that the skin does not match anything in 50 years of recorded physics. That is the level of shock researchers faced, not because the material was conclusively artificial, but because it was utterly unaccounted for. If it is natural, it is a form of nature that has not yet been observed directly. If it is ancient, it carries memories of stellar destruction, predating our galaxy's modern structure. And if it is something else, that possibility remains unspoken, not rejected, but held carefully at a distance. The polarization anomaly also fits with other traits. A high nickel surface would scatter light in unusual ways. Metallic dust can produce signatures unlike traditional cometary grains. A smooth, erosion-resistant crust could explain the lack of tail and the hidden mass loss. The pieces begin to align in a quiet, unsettling way. Nothing about 3I Atlas seems built in the environments we know. Everything about it hints at extreme origins: pressure, heat, age, and physical conditions that lie outside our normal experience. For scientists, the feeling is not fear, but awe. The sense of looking at something so old and so unusual that it breaks the limits of current textbooks. 3I Atlas does not behave like a visitor from another star system. It behaves like a visitor from another era of the universe. An era when matter formed differently, when stars lived violently, and when the building blocks of planets were still settling into their present patterns. And yet the most startling clue was not just the material itself, but the direction from which this strange object arrived. Because even its path through space seemed woven into a mystery astronomers have been trying to decode for nearly half a century. Even its direction in space connected to a long-standing mystery. When astronomers traced the incoming path of 3I Atlas backward through space, they found something that made them stop and look twice. Its trajectory, when extended far beyond the planets, points broadly toward the constellation Sagittarius, a dense, ancient region of the sky filled with star clusters, dust lanes, and the crowded core of the Milky Way. Sagittarius is enormous, so seeing an interstellar object come from that general direction is not surprising on its own. But within that expanse lies a much smaller, much more peculiar landmark. The same region of sky associated with the famous 1977 WOW signal. That short, unexplained burst of narrowband radio energy remains one of the most debated anomalies in the history of SETI. It was never repeated. It remains unresolved. And its origin was traced to a point in Sagittarius. Not a pinpoint, but a patch of sky only a few degrees wide. The path of 3I Atlas does not pass exactly through that patch, but the alignment is uncomfortably close. A difference of only about 9 degrees separates the incoming direction of the object from the central estimate of the WOW signal's source. 9 degrees in a galaxy of billions of stars. 9 degrees in a sky that covers 41,000 square degrees. Not close enough to claim any connection, but close enough to raise eyebrows. Space is big. Coincidences this precise are rare. Researchers are careful with this kind of detail. Trajectories blur across long distances. Small uncertainties compound over light years. No responsible scientist claims that 3I Atlas has anything to do with a radio burst received almost 50 years ago. And yet the juxtaposition lingers. An interstellar visitor exhibiting unprecedented behavior. An arrival route pointing near one of the most mysterious signals ever recorded. A coincidence that sits just close enough to feel uneasy, yet far enough to deny conclusion. The effect is not to suggest intent, but to evoke scale, to remind us how vast the universe is, and how unexpected alignments can still happen. But it also strengthens a feeling that has been growing through every anomaly discussed so far. Something about this object keeps lining up with the edges of our understanding. Its chemistry, its motion, its mass loss, its path. Each detail occupies a narrow region between the expected and the extraordinary. The arrival from Sagittarius adds another layer. The sense that we are seeing a pattern, even if the pattern is nothing more than the human mind connecting dots in the cosmic dark. But the coincidence remains on the table, impossible to ignore, impossible to prove, hovering in that strange gap between curiosity and caution. Is it a coincidence or a pattern? The question hangs in the silence of deep space, and the last anomaly was its strangest behavior yet. In the days leading up to its closest approach to the Sun, 3I Atlas displayed one final behavior that pushed it far outside the boundaries of known comet physics. Telescopes that could still see it, mainly space-based instruments and data relayed from Tianwen-1, recorded a sudden, dramatic surge in brightness. Not a gentle rise, not a gradual warming. A spike, a flare, a jump so steep that it stunned astronomers analyzing the curve. It brightened faster than 99.9% of all comets ever observed. Comets brighten as they approach the Sun because their icy surfaces begin to sublimate, releasing gas and dust. This forms a glowing coma, which expands and reflects more sunlight. The process is predictable enough that astronomers can model brightness curves with high accuracy. Almost every comet falls somewhere along those familiar curves, some brighter, some dimmer, but nearly all within the same family of behavior. 3I Atlas did not. It brightened far too quickly, and in a color balance that made even seasoned researchers pause. The emission leaned strongly toward green, more intense than typical cyanide-driven green comas seen in active comets. This green glow grew and sharpened until, for a brief window, the object resembled a concentrated emerald spark drifting near the Sun. But just as quickly as the flare appeared, it vanished. When 3I Atlas moved away from the Sun, its brightness collapsed at a rate no model could account for. The decline was too steep, too sudden, as if the mechanism that produced the flare shut off abruptly instead of fading out. Normal comets cool slowly. Their comas linger. Dust continues reflecting sunlight for days or weeks. 3I Atlas dimmed in a fraction of that time, almost as if the flare had been a single event rather than a sustained outgassing process. This creates a perplexing contradiction. A flare requires mass loss, but earlier observations showed almost no visible dust, and a post-perihelion fade requires exhaustion of material. Yet the speed of the decline suggests that whatever brightened the object was both brief and tightly controlled. The light curve does not match any known comet. It does not even match unusual comets. It stands alone. The green wavelength dominance complicates things further. Green emissions typically arise from diatomic carbon or cyanide excited by sunlight, but the ratio recorded from 3I Atlas did not match normal proportions. It was too bright, too well-defined, and not accompanied by the expected secondary colors. It was a spectral fingerprint without a template, another entry in the growing log of anomalies. As astronomers plotted the brightness curve on a timeline, the graph looked less like the familiar rise-plateau decline of comet behavior and more like a sudden pulse, a flash in the dark. One researcher described it as a signal without a sender, meaning that the rise and fall were so abrupt they resembled an event rather than a chemical process. Something triggered the brightening. Something ended it. And whatever that something was, it followed none of the known rules. For the scientists who had been tracking 3I Atlas from the moment Tianwen-1 captured it, this anomaly was the final stroke in a portrait that already defied explanation. A tailless comet losing billions of tons of mass. A silent acceleration without visible cause. A trajectory aligned with the plane of the planets. A sunward jet that should not exist. A size-speed profile that broke statistical norms. A nickel-rich chemistry more ancient than the solar system. A nearly waterless structure. A surface scattering light in ways no comet ever has. And now, a brightness curve that reads like a heartbeat in the void. Put together, the odds become impossible. By the time the 10th anomaly was confirmed, astronomers began to confront an uncomfortable truth. None of these behaviors, taken individually, were expected. But taken together, they were almost impossible. Each trait, the missing tail, the invisible acceleration, the perfect ecliptic alignment, the sunward jet, the oversized core, the extreme nickel content, the near absence of water, the unprecedented light polarization, the Sagittarius approach, and the emerald flare, carried a probability so small that researchers struggled to fit them into any familiar model. Comets can be strange, yes. Interstellar objects can be stranger. But the likelihood of one object displaying all of these traits at once drops below 100,000th of a percent. Less than 0.01%. Less than the chance of randomly assembling a functioning watch by shaking loose gears in a box. Less than the chance of two unrelated stars eclipsing each other from Earth's viewpoint on the same night. This is why even cautious scientists began using phrases they normally avoid. Not dramatic language, not speculation, but statistical descriptions that carried a quiet weight. One researcher summarized it in a way that resonated through the community. This is a statistical outlier of the universe. The deeper problem is not the rarity. Rare objects happen. The problem is coherence, the way each anomaly deepens the next. The chemistry supports the polarization. The polarization supports the mass loss mystery. The mass loss mystery supports the acceleration. The acceleration supports the size-speed contradiction, and the trajectory threads through them all like a line drawn with deliberate precision. At a certain point, improbability becomes its own phenomenon, something that forces scientists to ask whether the frameworks built for ordinary comets and ordinary physics can stretch far enough to hold a relic from a different era of the cosmos, or something shaped by conditions we have yet to imagine. And so the question rises naturally from the data, not from speculation. If 3I Atlas is not behaving like a comet and not behaving like a typical interstellar fragment, then what could it actually be? So what could 3I Atlas actually be? With all 10 anomalies laid out, astronomers faced a crossroads. Either 3I Atlas is the strangest natural object ever recorded, shaped in a corner of the universe where physics plays by harsher rules, or it is something else entirely. The challenge is not to leap into speculation, but to examine the possibilities with the same discipline that uncovered the anomalies in the first place. Two broad scientific scenarios emerge, each with strengths, weaknesses, and unanswered questions. The first is the natural scenario. In this view, 3I Atlas formed in a star system far older and more violent than our own, perhaps a system that existed shortly after the universe's birth, where temperatures were higher, pressures more extreme, and the materials produced by collapsing giant stars were distributed unevenly through space. In such a setting, it is possible, though rare, for objects to develop with high nickel content, low water levels, and surfaces coated in coarse metallic grains. If the fragment originated near a population 3 supernova, the extreme conditions could explain its unusual chemistry and the strange polarization of its reflected light. Its age, estimated at over 13 billion years, would have given it unimaginable time to drift between regions of the galaxy. Over such timescales, erosion from cosmic rays could harden its surface. Impacts with interstellar dust could polish its exterior. The cumulative effects of billions of years might create a smooth, erosion-resistant crust unlike anything we have seen. Even the lack of a tail might be attributed to heavy, non-volatile material shedding in ways that do not scatter light. Natural processes can stretch far when pushed to cosmic extremes, and yet this scenario leaves holes. The missing tail, the invisible acceleration, the sunward jet, the statistical unlikelihood of its aligned trajectory, the green flare. These behaviors remain hard to connect to any known physics, even with generous allowances. The natural scenario explains the age and composition, but struggles to unify the rest. The second scenario is more controversial, not alien spacecraft, not deliberate design, but the possibility that 3I Atlas is an artificial relic. Not something active, not something controlled, but a fragment of material shaped long ago by intelligent hands, drifting now as a dead or dormant artifact of a civilization lost to time. This idea exists not because scientists want it to be true, but because a handful of the object's features are difficult to reconcile with natural formation alone. Metal-rich composition, smooth profile, directional behavior, non-gravitational acceleration without visible cause. These traits resemble characteristics of engineered structures, even if produced unintentionally, such as panels, shells, or layers built for extreme environments. Some researchers note that engineered alloys can produce extreme polarization signatures, similar to those seen from 3I Atlas. Others point out that a structure designed for high durability could survive billions of years in interstellar space when a natural comet would crumble, Harvard astrophysicist Avi Loeb, known for his work on interstellar anomalies, often emphasizes a balanced approach. Do not assume artificiality, but do not rule it out prematurely. In his words, extraordinary claims require extraordinary evidence, but refusing to consider them is unscientific. If 3I Atlas were an ancient fragment of a long-extinct civilization, a shard of a probe, a piece of shielding, or a remnant of a forgotten technology, it might naturally explain the nickel-heavy structure, the erosion-resistant surface, the directional jets, and the peculiar acceleration. Yet even this scenario is incomplete. There is no sign of deliberate signaling, no radio emissions, no clear geometric structure, nothing that undeniably points to technology. Much of what appears unusual may still be the product of environments humanity has never witnessed. In a universe of 2 trillion galaxies, filled with places we have never seen, and conditions we have never modeled, nature might still be capable of producing objects that mimic engineering by accident. And so neither explanation stands alone. The natural path explains the origins. The artificial relic path explains the behaviors. Both fall short, both answer half the riddle, and both remain open, suspended in that strange region where data meets imagination. To move forward, scientists realized they needed to ask a deeper question. Not what 3I Atlas is now, but where it came from. The key to understanding its nature lies not in the present, but in the earliest chapters of cosmic history. To answer this, we must go back in time, way back. To understand what 3I Atlas truly represents, we have to step far outside the boundaries of our solar system and far back in time. Not millions of years, not billions, but almost to the very beginning. Picture the universe when it was young, raw, and unrecognizable. A time when the first light had only recently broken through the darkness, when no galaxies had fully formed, no planets had yet coalesced, and the chemical ingredients of life did not exist. This is where the story begins. Roughly 13.4 billion years ago, a mere 300 million years after the Big Bang, the universe entered what astronomers call the cosmic dawn. Temperatures had fallen enough for hydrogen and helium to collapse into the first stars. These stars, known as population 3 stars, were nothing like the calm, steady suns we see today. They were enormous, short-lived giants, burning hotter and brighter than anything in the modern cosmos. Their lives were measured not in billions of years, but in millions. Their deaths were spectacular, explosive events that forged the universe's very first heavy elements. Before these stars existed, there was no iron, no nickel, no carbon, no oxygen, no familiar chemistry. Everything we know, planets, comets, oceans, mountains, people, depends on the metals first created in the hearts of those early giants. When they collapsed, they seeded space with fragments of newly minted elements. These fragments became the raw grains from which future stars, future planets, and future galaxies would form. And this is where 3I Atlas re-enters the story. The nickel signatures found in its spectrum, the inverted ratio, the metallic dominance, the coarse grain polarization, match the kinds of element mixtures produced in those early supernovae, the kind that no longer occur in the modern universe. To find a fragment carrying this fingerprint is to hold a piece of cosmic archaeology. A shard forged before the Milky Way existed, before the spiral arms took shape, before our sun was even an idea in a collapsing cloud of dust. Imagine the journey. A chunk of material blasted outward by an ancient star, cast into a universe still assembling itself. It drifted long before galaxies collided and merged, long before Earth cooled from molten rock, long before the first microbes stirred in our oceans. Across billions of years, it survived radiation, shock waves, and wandering encounters with stellar winds. Most fragments from that age would have been shattered or eroded to dust, but a dense, nickel-rich core, hardened by heat, pressure, and time, could endure. This is one reason why many scientists cautiously support the natural ancient origin scenario. The chemistry aligns beautifully with the idea of a primordial relic. The polarization matches expectations for rough metallic grains shaped in extreme environments. Even its unusually smooth profile could be explained by eons of micrometeor polishing in interstellar space. It is a lone traveler from the universe's childhood, preserved by the vacuum and carried for billions of years on a trajectory shaped by nothing more than gravity and time. But the age itself is the most staggering part. If the spectral interpretations are correct, 3I Atlas is not just older than the solar system, not just older than the planets. It may predate the Milky Way's earliest generations of stars. In the words of one astronomer who reviewed the compositional models, this object may have formed before the Milky Way existed. That is the scale we are dealing with. Not planetary time, not stellar time, but cosmic time. This perspective reframes everything. The missing tail, the strange acceleration, the sunward jet, the extreme polarization, all become secondary to the central fact that we are observing something from an era of the universe we have never directly touched. An era when physics operated at different intensities, when matter was young, when the rules of formation were harsher and more chaotic. It is possible, perhaps even likely, that behavior which seems unnatural to us simply belongs to natural processes that occurred in those violent conditions. And yet, the sense of wonder does not fade, because for a brief moment in human history, this relic from the universe's first generation of stars passed silently through our neighborhood. It was here, beside our sun, briefly illuminated, briefly recorded, briefly understood, before resuming its long, ancient journey across the darkness. And now, this relic begins to leave us. As quickly as it arrived, 3I Atlas is now slipping away from us. Each passing day carries it farther from the sun, farther from Mars, and farther from the instruments that briefly traced its path. The same unexplained acceleration that puzzled scientists on its inbound journey is now guiding it outward, nudging it toward the deep, cold frontier beyond the planets. Its speed is rising to the point where even the sun's gravity can no longer hold it. Once it crosses a certain threshold, it will be gone, permanently. Objects on escape trajectories do not return. They do not loop back. They do not offer second chances. 3I Atlas will pass the orbits of Jupiter and Saturn, then the Kuiper Belt, then the distant shell of frozen bodies that mark the solar system's edge. After that, it will re-enter the interstellar medium, the endless ocean between the stars. From there, it will continue drifting, silent and solitary, for millions or billions of years. Future civilizations, if they exist, may never detect it, and humanity will never see it again. There is a particular sadness in this. For a brief moment, this ancient traveler brushed our world. It came close enough for our machines to capture its shape, its motion, its impossible chemistry. We gathered everything we could: images, spectra, brightness curves, polarimetric data. But compared to the full story of this object, what we collected is only a handful of pages from an epic written across cosmic time. The rest of its journey is locked within the object itself, in the metal grains of its surface, in the memory of collisions etched into its crust, in the secrets of an age before galaxies matured. As 3I Atlas fades into distance, the signal weakens. The reflective spark dims. Instruments struggle to track it against the black backdrop of the outer solar system. Soon it will be too faint for any telescope to follow. The data we have now, the strange polarization, the ancient nickel signature, the vanishing tail, the sunward jet, will remain the only record humanity will ever hold. No future mission will intercept it. No spacecraft will chase it. The opportunity has passed. And yet, knowing this adds a kind of quiet beauty to the story. Not everything in the universe is meant to stay. Some things come close only long enough to be noticed, to leave a question, to spark imagination. And then they move on. 3. Atlas is one of those things, a visitor that brushed the edges of our understanding before returning to the deep silence between the stars. But this is only the beginning. Even as 3I Atlas fades into the dark beyond our reach, its brief appearance marks the beginning of something far larger than itself. For most of human history, we studied only the objects bound to our own sun. Planets, asteroids, comets, icy fragments from the outer reaches of our system. Interstellar visitors were so rare that many astronomers doubted we would ever see one. Then, in just a few years, 3 arrived. Not because the universe suddenly changed, but because our tools finally became powerful enough to notice them. The next chapter of this story will be written by a telescope unlike any built before, the Vera Rubin Observatory. When it becomes fully operational, it will scan the entire night sky every few days with unprecedented depth and precision. Instead of catching only the brightest or closest objects, it will detect faint, fast-moving visitors that once slipped past unnoticed. Models suggest it could find dozens of interstellar objects every year, a flood compared to the handful we've seen so far. And with each new detection comes a new opportunity. Some visitors will be pristine, icy bodies from distant regions around other stars. Others may be fragments of shattered planets, pieces of ancient stellar explosions, or relics from epochs when the universe was young. Among them may be more objects like 3I Atlas, metal-heavy, ancient, and enigmatic. With modern instruments ready to analyze them, we may finally piece together the full history of the galaxy's earliest generations of stars. This is what makes the future so exciting. For the first time, astronomy is not limited to studying our own solar system. We are beginning to collect samples, not physically, but through light and motion, of places we will never visit. Every interstellar object carries information about the environments that shaped it, and the more of them we observe, the clearer the patterns become. Composition, structure, age, trajectory, polarization. These clues, gathered across many visitors, will eventually reveal what is normal and what is extraordinary. In that sense, 3I Atlas is not an isolated mystery. It is the opening chapter of an entirely new field, a preview of discoveries still to come, a reminder that the galaxy is filled with debris from forgotten eras and distant worlds, drifting silently until one of them happens to cross our path. What was once a curiosity is becoming a frontier. What was once a rare occurrence will soon become routine. Interstellar astronomy has only just begun, and this brings us to our final question. In the end, 3I Atlas leaves us with more questions than answers. But perhaps that is exactly the gift it was meant to bring. A reminder that the universe is older, stranger, and far more layered than the sliver of time we occupy. Over the course of its brief appearance, it revealed 10 extraordinary anomalies: a massive loss of material with no tail, an acceleration with no visible force, a trajectory aligned perfectly with the plane of the planets, a jet aimed toward the sun instead of away from it, a size and speed combination that defied expectation, a chemistry dominated by ancient nickel, a near absence of water, a polarization signature unlike anything ever recorded, an approach direction brushing the region of the wow signal, and a brilliant green flare that rose and vanished far too quickly. Each of these traits alone would make an astronomer pause. Together, they form a portrait of an object that sits at the edge of our understanding. Not supernatural, not science fiction, simply extraordinary, in the most literal sense of the word. A visitor shaped in conditions we have never witnessed firsthand. A relic forged in the early universe, wandering the galaxy for billions of years before passing close enough for us to catch a glimpse. The truth is that we do not yet know exactly what 3I Atlas is. It may be a natural fragment from a long extinct generation of stars. It may be a rare kind of metallic core hardened by cosmic time. It may even be something that challenges our assumptions about what nature can produce. But whatever it is, its arrival has expanded the boundaries of what we consider possible. It has reminded us that our maps of the cosmos are still in pencil, not ink. That the universe often behaves in ways that feel unfamiliar simply because its story is so much longer than ours. There is also a quiet beauty in the fleeting nature of the encounter. This object, older than the sun, older than Earth, older than the Milky Way's settled shape, passed within reach of our instruments just once. We watched it brighten, drift near the sun, flare in emerald light, scatter strange polarization into our detectors, and then fade back into darkness. We recorded everything we could, knowing the moment would never return. In that sense, 3I Atlas was not just a scientific mystery. It was a reminder of how brief and precious our opportunities to observe the universe truly are. As it departs, the question it leaves behind is simple and impossible to ignore. What else is out there? How many ancient travelers cross the galaxy unseen? How many relics of cosmic history pass silently between the stars? And how many more will we detect now that our tools are finally capable of noticing them? The universe has always been speaking. For most of our history, we simply lack the instruments to hear it. But now, with new observatories coming online, new missions preparing to scan the sky, and a new age of interstellar astronomy unfolding before us, we are standing at the threshold of understanding. We are not just observing the universe, we are finally listening to it.